All right, so we're going to take a look at stretches and compressions of functions today. You'll notice in grade 10, or the difference between your grade 10 lesson and today is last year would have been just vertical stretches and compressions, but this year we're going to take a look at vertical as well as horizontal, okay? And we're going to use some knowledge from grade 10, both in terms of vertical and horizontal, in terms of stretches. So we're just taking a look here at vertical stretches. Vertical stretches are going to be denoted by the variable A, okay? A is going to be the control factor for vertical stretches. So if A is greater than 1, the graph is going to be stretched vertically by a factor of A. And if it's less than 1, we're going to compress, which is very, well, it's identical to what you did in grade 10 with parabolas. The other thing we're going to do today is start looking at the other functions that we've kind of already had a look at in the course. Horizontal stretches, though. Horizontal stretches are a little bit trickier, only because the variable k is on the inside of the brackets. And we learned a bunch of stuff with the horizontal translations last year, and we also saw it the other day when we were looking at the translations lesson, that horizontal work always behaves in the opposite manner than what we think. And what we're going to try to do without convoluting the lesson is explain why. Okay, this 1 over k is the reason why. And it ends up spitting out the opposite of what you think is actually happening. So for instance, if k is greater than 1, the graph is going to be horizontally compressed. Okay, and if k is in between 0 and 1, so some sort of 0.5, for instance, would be between 0 and 1, or 0.75, 3/4, whatever. That's going to indicate a stretch horizontally. Okay, now how does that work? Well, I'll just do one here. Well, we can do both of them. So the compression, you'll notice if k is greater than 1, the graph is compressed horizontally by a factor of 1 over k. This is important, the 1 over k piece, right? So 1 over, let's say the k value in here, f is going to be 2x. The k value is the 2. Okay, so that's what's going to get put down here. And so you can see the compression happening, right? Whereas, if we use the same example, but this time, k is going to be between 0 and 1. So this, just for simplicity's sake, we'll use a half, right? Half would be between 0 and 1. So I'm going to put 1 over 2. And you can ask yourself, how many times does 0.5 go into 1? Well, it's 2, which is where this idea of a stretch comes from, okay, and it's behaving in the opposite manner. So if we come down and take a look at a couple examples here, right, I think what's important for you is to be able to identify A versus K, okay, and so if I'm looking at these, that's an A, that's a K. I know that that's the case because of, with a quadratic, the presence of the brackets. The brackets denote that there's the inside versus the outside of the function, okay? And we're going to see what that looks like with a couple of the other functions later in this lesson, okay? So this, again, is an A, and that is a K. Okay, so if I were to describe these, this would be a vertical stretch by a factor of 2. Okay, and for this one, this is going to be, because it's on the inside, anything on the inside is always horizontal. Horizontal something, translations, stretches, compressions, reflections, whatever it is. If it's on the inside of the function, in this case with a quadratic, inside is denoted with the presence of brackets. We're going to have a horizontal, now careful, it's not what you think it is, it's a horizontal compression here. By a factor of, remember, 1 over k. K being 2 in this question, right? So 1/2. It's a compression by a factor of 1/2. Okay, this, no brackets here. So this is a vertical compression by a factor of 2. Sorry, 1/2. Okay, and the last one, again, I see the brackets, okay, and it's going to be opposite because I see the brackets. So this is a vertical, sorry, not vertical. Brackets mean horizontal. So it's a horizontal stretch by a factor of 1 over k again, which if I'm really thinking about this is going to be 1 over 2, which is 2. Okay, so you get a horizontal stretch by a factor of 1 over k. When I substitute the actual k value in, it spits out the stretch component. Because it's always opposite. That's important to remember. Anytime you see any sort of transformation on the inside of the function, it's opposite, opposite, opposite. Okay, it's an easy thing to forget. Okay, so it looks like when I'm graphing, or whatever function I'm graphing here, it doesn't matter what it is, but in this particular instance, we have a quadratic, right? And so what I'm going to do always is graph the original. Okay, this would be the base quadratic. That wasn't very good. Okay, and that's your base quadratic. Draw it over there. All right. Okay, and we're going to call that f of x is going to equal x squared. Okay, it'll be done in the red. And also don't forget to label your axes. Okay, so with A is asking me to vertically compress the graph, right? By a factor of 1/2. Okay, so we're going to take all those points, right, and we're going to compress them or make the y values half as big. Okay, so the y value for that point is going to be positive 4, and so it's going to become 2. Okay, so we're going to go to there, and this is also going to go to there. This is going to go to 0.5, and that's going to go to, oops, this is going to go to 0.5. 0 stays at 0. You can see when I vertically compress a graph, it gets wider. Okay, so that would be the graph of, we'll call that g of x is 1/2 x squared. Okay, now we're going to forget we did the purple graph. Now we're going to go back for the next question. Okay, it's always in reference to our original red graph. Okay, so for this one, this is going to be, I see brackets. The brackets mean horizontal, so first word I'm going to write is horizontal. Horizontal something. Okay, and we're going to see that it's a horizontal. It's opposite because we use the word horizontal. It's a horizontal compression. And remember, it's 1 over k, which is 1/2. Okay, so we're going to compress by a factor of 1/2. That means that all, and horizontally, okay? And just to distinguish between the vertical compression by a factor of half and a horizontal compression by a half, we're going to see that the two graphs are kind of opposite, right? So the red graph, if it was a horizontal compression, horizontally being left and right, is now going to become skinnier. So this is 2 x units away. So if it's 2 and we cut it in half, it's now going to go to 1. The same thing's going to happen on the other side. Okay, 0 is going to stay at 0 again. And so you can see there is a horizontal compression of that red graph. We'll call that h of x is going to be 2x. Oops, I missed a squared on that other one. Okay, so that is pretty much it. And that's on something that you've seen before. I mean, the purple graph should be something that you would have done in grade 10. That should not be new. What is new is the blue graph. Okay, this concept of horizontally compressing or stretching. Okay, the second page we're going to take a look at. So this is grade 10 content for the most part, something that you should be familiar with. We're going to come down here and take a look at a couple of the other graphs that we've done this year. Okay, so again, we're just going to label our axes before I forget. Okay, this graph here is what we call the root function, the square root function, right? And so with the root function, you always have the base. We had 3 major points with this graph, right? 0, 0, 1, 1, and 4, 2. Those are strategically chosen inputs of x so that I get nice values of y out. So those points would have been 0, 0. If I input 0, I get 0 out. If I can input 1, I'm going to get 1 out. And if I input 4, because 4 square rootable, nicely, I get 2. So that's where those points came from. Okay, so same thing, we're going to do the exact same work that we just finished doing. Okay, so in in the top equation, that's a vertical stretch by a factor of 2. Okay, and so let's vertically stretch this graph by a factor of 2. So 0 is going to stay at 0, 1 turns to 2, and 2 turns to 4. Okay, that would be the graph. G of x is going to equal 2 root x. Now, if you didn't have different colors, you'd mark these on the graph. Okay, but you could call it, and just clearly, again, we're just trying to emphasize the function notation too, right? Like, it's nice because you can call that f of x, very quickly be able to identify graphs, g of x. Okay, especially if the questions didn't have that y equals, you could call them g of x, h of x, f of x. Very clear there. Okay, so for the next one, this is an example of, there are no brackets there, but you have some sort of control factor on the inside of the function. Okay, again, inside, horizontal. Okay, and horizontal, as soon as you write that word, you got to know it's opposite. Okay, so we know that it's a horizontal stretch by a factor of 1 over k, and in this instance, 1 over k turns into 2. So it's a horizontally stretched by a factor of 1 over 1/2, which is 2. Okay, so again, we're going to horizontally stretch the red graph, okay, our base graph, not the purple one. Okay, now if you had a big long list of transformations, as we're going to see tomorrow, or in the next lesson, then you can start doing, like you transform the red graph to be the purple one, and then we would transform the purple one into the blue one, and so on. You just follow the sequence of transformations that are on the function. But because this is one question, and this is one question, we're always referencing the base graph of the red one for now. Okay, so we're going to horizontally stretch that red graph. So if we're 1x unit away from the y-axis, then it's going to go to 2. And if we're 4 away here, it's going to go to 8. And 0 is going to stay at 0. So we get that graph now. So that's h of x, where h of x is equal to 1/2 x, square root of 1/2 x. Okay, so very important that you conceptualize the last lesson and this one individually, because we're going to put them together in the next one, and you're going to have all 6 transformations for one graph. Okay, so we'll do one more, and then that'll be that. Okay, so this is another function that we've seen recently. This is the absolute value graph. Right? What does the absolute value graph look like? Well, like this. It just simply states every input you input into there, positive or negative, yields a positive output. Okay, so there's your graph of f of x. Okay. Okay, and then what are we doing here? Well, this is a horizontal, or it's been horizontally stretched by, again, a factor of 1 over k, where, okay, 1 over 1/3 turns into 3. Okay, how many times does, so just to conceptualize that in case you're stumped on that, it's technically 1 divided by 0.333333. So how many times does 0.333333 go into 1? 3 times, okay? Another way to think about that, and the preferred way would be to, you know how to deal with fractions inside of fractions. It's 1 multiplied by 3 over 1. We bring the denominator up and multiply by the reciprocal. Okay, that's also where the 3 comes from. Okay, so we're horizontally stretching this graph. So again, if we're 0 is not going to go anywhere, but if we're 1 unit away in the x direction, it's going to go to 3. And if we were 2, it's going to go to 6. Okay, and because it's symmetrical about the y-axis, same thing happens on this side. Oops, to 3. And 2 goes to 6. Okay, and if I connect those points, this is our new function. Struggling with the connecting of the points. Okay, so that is the graph of, we call it g of x, where g of x is 1/3 x. Okay, so hopefully that makes some sense to you, and a little bit of practice, it shouldn't be too crazy, okay? Important for you to conceptualize that, because we're just going to put them all together. You're going to have to be able to identify A, K, H, Q, and the reflections in the vertical and horizontal directions. Okay, so that's it for the lesson today. And tomorrow's lesson, we'll start putting it all together.